So, hello everyone. Good morning, good afternoon, and good evening. In our first lecture today, we have the honor of welcome Professor Dr. Rodriguez Ramos. Currently, he is a visiting professor at Fluminense Federal University, UF, and a member of its graduate program in computational modeling. Today, Professor Rodriguez will speak about computational homogenization for the estimation of overall properties in linear viscoelastic composite. Professor Rodriguez, thank you for accepting our invitation. The floor is yours. Thank you very much.
Thank you. Vou começar a falar algumas coisas em portunhol. Eu agradeço muito o convite que passou o professor Juan, também a professora Sandra e a Mauro. Agradeço muito, para mim um grande honor ficar aqui com vocês no seminário, que é um seminário internacional. Eu comecei a ver que este seminário existe pela rede e o Amaury, que conheço de os estudos anteriores, falei com ele e ele me convidou para fazer esta pequena apresentação. Agradeço muito o tempo de Sandra e de Juan pela organização deste magnífico e interessante seminário. Também a presença de cada um de vocês, que para mim é muito importante. Agora vou começar a apresentação e vou falar um pouco well, this is a joint work in the last years that we have done with people from other university in Mexico, for example, and now together with people from here, from Brazil. Panthers, who is one of them in UFI, and Joan and Jose Antonio Otero, who are professor from Mexico University, as you can see there. Well, talking about motivation, viscoelasticity has different and important motivation in the real world, like you can see in human bodies, tissues, soft tissues, aeronautic, and so on. So, the most important is that sometimes we need to create models, different mathematical models, for representing the characterization of such, let's say, materials. In bones, in particular bones, like you can see here, has these, let's say, properties, like viscoelasticity. Also, skin, as you can see here in the figure, is a typical and real example of, let's say, viscoelasticity. In general, when we talk about viscoelasticity, we consider that it is a combination of a dashpot with a spring. One is under the Hooke's law, and the other is from Newton's law. Therefore, combining these different types of effects by, let's say, Hooke or Newton's law, we can consider different models like a Maxwell, Kelvin, and so on. In general speaking, we can say that, for instance, one-dimensional viscoelastic model, which is very well known in the literature, is Kelvin-Boyd's model, represented by this configuration of stresses and strain. In general, we will talk about, let's say, what we can say, this is partial differential equations, in general speaking. In particular, when it is viscoelasticity, we have integral equations, which obey, in our case of analysis, the Boltzmann principle. R and G are two functions that denotes the kernels. Sigma and chi are, let's say, stress and strain. Because we consider in our examples and analysis no agent viscoelastic material, then we consider formulas like for the relaxation and creeps, formulas like that. In particular, in order to analyze the microstructure of the material, because we are talking about viscoelastic materials, which are in general very heterogeneous, means that they have different microstructures, we consider a separation of scales. In particular, we can use two scales, epsilon1 and epsilon2. L capital letter is the length, the general length of the body, and L1 and L2 small letters are the dimension of the microscale. We consider in that case generalized periodicity. The definition is given like that, and the two different scales different, and we denote here like Y and Z, and is, let's say, the physical variables that concerns in that case or are related to the microstructure with Y and Z. Rho, which is introduced here in Formula 4, by rho, we will consider later, we will mention like a certain stratified function. The stratified function obeys certain laws that we will show, and in that case, rho Y and rho Z deform in certain sense the body and the surface of the body. Three scales is basically introduced. Y and Z are, let's say, the micro scale, and X is the macro scale. Then we consider macro model, where the microstructure are should be, for instance, particles, porous, or let's say fibers, reinforces of the body. And rho is what I mentioned, a stratified function. The general algorithm is written here. We have the methodology, the formulation of the problem. We consider and we apply the Laplace-Carson space. Asymptotic homogenization is the method that we will apply in order to obtain local problems, homogenized problem, and effective coefficient. Analytically, sometimes we can solve the problems, or in case, more complicated case, where the microstructure is very complex, then we apply a certain numerical method of solvers, like ANSYS, CONSOL, and so on. This is in general the strategy that we will follow for the analysis of our problem. And the formulation of the problem is here. All are partial differential equations given by the boundary condition, 5B, C, and D. Here is declared what is the variables, displacement, external forces, normal, and all the variables involved in equations 5 are here very well denoted. And 5, in the notation, assume that in that case is periodically with respect to Y and Z. Then the structure that we consider is basically, let's say, periodically in the two variables, y and z. Here you can see what we call in mechanics, in solid mechanics, we call that this is the constitutive relation, means the relation between the stress and the strains given by the integral. This is a Volterra integral that depends on time. And for that reason, we consider viscoelasticity, because this is a rheological problem, means the properties, the material properties, are depending on time in general. And here by chi is the Cauchy relation, very well known in terms of mechanics. And this is the boundary, the continuity conditions. When brackets, double brackets here means a jump at the interface between different media. This is a jump, and we will see the jump in what form we consider. And the reformulation in terms of the Laplace-Carson of each problem. Here is the Laplace-Carson introduced for the calculation using the correspondence principle. Correspondence principle is that we have the statement of the problem in terms of time, and it is equivalent to a linear elastic problem using the Laplace-Carson. This is more or less the idea. And then in terms of the Laplace-Carson, the original problem mentioned previously can be rewritten in that form, like equation number 9 is represented, and the interface contact condition using brackets for, let's say, simplicity in the notation is given like that. This is a jump. Then the homogenization process, or the procedure for the homogenization, means that you have a real body like that, reinforced. This is, let's say, one view of the real material. This is reinforced by fibers, cylindrical fibers. B is what we call it unit periodic cell. This is a cell that leads to the analysis of in the homogenization process. And number C is an equivalent homogeneous structure. Means the homogenization process allows us to a very real heterogeneous material to, let's say, to reduce in certain sense to an homogeneous structure, which is equivalent to the original. But the properties here in the homogeneous depends on the microstructure, directly depends on the microstructure. This is a general idea, very rough idea of the homogenization process. And we need to introduce certain steps for the homogenization method, like you read here, we need like use the people from numerical method, in particular finite element method, RVE. RVE is a representative volume element. We apply the average operator. We calculate the fields, mean displacement, stress, strain on the RVE, and we also calculate and determine the composite effective property given by certain relations that we will see. In order to follow that steps, we introduce the RVE in a very simple way, like a cube, and the fast variable y is the global variable x divided by epsilon. Epsilon is a very small parameter. This is epsilon is a geometric parameter that we introduce geometrically from a general view of the problem. We expand for 3 scale, means X, Y, Z, and S is the Carson, Laplace-Carson barrier, and then we expand the displacement like that, and using this expansion in terms of this parameter, small parameter epsilon that you can see here, and then using that expansion, we have different level of the hierarchical structure. The first level is epsilon 1 structure, and it is the main contribution given, and the operator, when I mentioned before, the average operator is given like that. In general, in very general, because here we are, let's say, calculating for a geometrical shape that should be cylindrical or spherical, and for that reason we have here the metric tensor G applied. In general, this is the main contribution for the first level. Second level is as well given here, and the boundary conditions are in that case written in that form, like 18, 19, and 20. And this is the relaxation modulus for the hierarchical case. Notice that R asterisk depends on R chapo or R hat, like you can see here, R hat in that form in number 14. And if you calculate R hat in 14, then you plug in here and you can calculate the overall property R. This is a general idea, but the numerical algorithm that we have used is the inversion of Laplace transform, the MATLAB functions, InverLab, and GAFTech is employed, and we have the numerical fundaments here in those contributions that it is written here. And in general, it is very important for laminate composite materials. It is one example that we are considered. The laminate means that we have a structure like a wood, for instance. Wood is one example of such laminate that for each layer perpendicular to one axis, you have the composite made. Each layer is made of certain material, and this is in general the, let's say, the effective coefficient written before in a very compact form. Now we have developed in certain form, and then you have R hat, and here is the expression for, let's say, R asterisk. Let me tell you that those formula 22 and 21 are the expression, the new expression for the homogeneous material previously mentioned, and in that case mathematically calculated. In order to give one idea of application, the 3 scale is applied, for example, the Dermis. Dermis is considered non-agent linear viscoelastic, and in that case with isotropic constituents. The two-phase composite is the collagen and ground substance. The ground is a viscoelastic constituent. All these properties are here summarized in table 1. The papers that Benitez, Montans, and Suan Lu are provided the materials parameters, and here we use the Prony series for the calculation. The calculation are the material parameter for gram of substance is here using the Prony series, and we are taking the Prony series for emice Dermis. sometimes you know that it's very difficult to find real material parameters already characterized. It is a problem that sometimes we have from the mathematical modeling. You create the mathematical model, but we need to introduce certain input parameters, and we have to plug in the input parameters with the real materials, and it is sometimes very difficult. Then we use this stratify function like that, using in 24. We use also Cartesian coordinate system. For that reason, the metric tensor is delta Dirac, and the wavy effect is given by that stratify function, and we use that stratify function because the Dermis has such a structure. Geometrically seems like that function. This is, of course, an idealization of the Dermis, but looks approximately the same. In the left part is a real structure of Dermis. The right is a modeling of that using that stratify function, and this is the behavior of the relaxation moduli in this case. This is R is the relaxation, and G is, let's say, what we call the inverse of the relaxation model. Later on, we cross to other situations where it's a little more complicated in the sense of the solution of the local problems, which are partial differential equation, in particular integral differential equations, and we consider, let's say a cell, a material, a composite reinforced by cylindrical fibers, cylindrical and unidirectional fibers distributed in two different cells, a square and hexagonal cells. With these two different configurations of the cells, we consider different distribution or arrangement of the fibers, like you can see here. The formulas calculated by the asymptotic homogenization to scale two fibers, two-phase fiber viscoelastic composite. Each one phase isotropic and the other is viscoelastic, you will see. And here it is the formulas. The formulas are in 25, are given a good idea and a good, we can say that it is close formulas, because here you can calculate the properties of the material with K, L, N, P, M, and prime. We denote what we call sometimes the materials parameter, like you can see here, R11, R12, 313, and so on. This is for simplicity. And for the square, we use these input parameters of the arrangement of lattices, because we have to use a lattice for the distribution, and hexagonal is here. They are reported in different papers by the author. And here we compare the numerical results. The comparison is based on a Bamush model reported by Tan and Felicelli. Bamush is variational method, unit cell homogenization. This is a very interesting method, and we compare our calculations provided by homogenization with the variational method of the unit cell. And the materials parameters introduced are elastic, fibers, and we have, for the matrix, we have the parameters here. Matrix is viscoelastic, fibers is elastic, and here you can see the comparison of the effective module and the square unit cell is used in this computation. And here in the superior part, we are identifying the volume fraction for the three curves. Red is 0.2, 0.4, and 0.6, different colors, and with circles are Bamuch. Bamuch, let's say, and asymptotic homogenization is more or less the same. We can say that. In the literature, you can find also different curves. Kernels, different kernels for viscoelastic properties, kernels Maxwell, Rabotnov, and so on. In particular, when t is equal 0, means time is 0, we can understand that we are in case of pure elastic situation. And for that pure elastic situation, we compare with other contribution of Luciano, 1994, and Barbero published his paper, or their papers, and we consider that values reported in that paper with asymptotic homogenization, and then for that limit case, when t is equal to 0, this is pure elastic, and this is the contribution reported by asymptotic homogenization. And in the other case, when times is changing from 0 to 300, we compare with that paper, other paper, 1995. They published that other paper, and this is for viscoelasticity, and we compare with that for different volume fraction, and you can see the comparison, how is doing and how is, let's say, reported here in that figure. Following that, we consider also other type of numerical homogenization method. The contribution is using with people from Germany. We have a good collaboration in the last years, and they make the calculation using finite element method. They know better than us how to find the effective property using finite element method for this numerical homogenization, and they made the calculation in that case for, let's say, the unit cell reported here, and they used the finite element package of ANSYS, in particular APDL, which is famous between the people from finite element method, and we reported that in one paper, the comparison that we had done with them for, again, for the Prony series using Laplace-Carson. We have the calculations made. This is the input material parameters used. This is elastic fiber with a viscoelastic matrix, which are here given. And here we have the comparison between asymptotic homogenization method, the numerical homogenization reported by finite element method people from Germany, and we compare with Luciano and Barbero 1995. It is a brief idea of the relaxation moduli. This is the whole characterization of that composite is here, and we have R11, 12, all. And therefore, for porous viscoelastic, we can mention also that we compare with asymptotic homogenization with numerical homogenization, and also with the results obtained by Magus and Creus in 2003. Here it is for the square unit cell, let's say. Then Following that, also for the hexagonal unit cell, we have the calculation. We have for the square and unit cell for both. Later on, we shift or we extended the result to fiber viscoelastic or Visco-piezoelectric because it has different applications. And for Visco-piezoelectric composite, we use also, in that case, we use the effective field homogenization, and the kernel is what people knows like a Rabotnov kernel, or we can say that it's a fractional kernel, is called like a fractional kernel. And using that fractional kernel and the effective field homogenization together with the asymptotic homogenization, we compare, this is the effective field reported here, the calculation. Here we can see 37, 38, 39, and the materials parameters used in the computation is titanato de baño and viscoelastic matrix.
A ver, chicos, en este ejercicio tengo dos respuestas que me indican que es la D, 37 millas.
And the numerical examples is here. This is a comparison, a direct comparison, asymptotic homogenization on effective field. Effective field, let me mention that this is a joint work that we did with Professor Levin from Russia. We did that work with fibers composite, and one application is the electromechanical coupling coefficients. This is very important for application in, let's say, sensors, or let's say in biomedical applications, we use that. This is an ultrasonic transducer. We use the behavior of the ultrasonic pulse echo transducer for medical purposes, and these two parameters are very good for that ultrasonic transducer. And the limit case is here, and of course that we have advantage and disadvantage of the asymptotic homogenization, and for that reason we try to introduce a 3D problems, which is here very brief. I will mention because the time is short, and in that three-dimensional computational, we extended for console multifixes. It was given by one former PhD student that we had, Cruz Gonzalez, and he made all these calculations using a console, and it is the discretization that we use it for the mesh. And in general, I could say with this presentation that the two-scale is applied. Later on, we can introduce three-scale model for, like, let's say, a generalization of previous two scales. We derive the local problems and analytical expression, and using Prony series, numerical computations are shown, also based on Laplace-Carson transformation. We have comparison, a good benchmark with theoretical models are provided, an extension to the effective field and asymptotic homogenization for computing effective model in viscoelastic piezoelectric composites are provided here. The composite is formed by transversal isotropic piezoelectric inclusion and viscoelastic matrix, which is important for transducer applications, and we provide closed form for the effective module in all the cases. A Rabotnov fractional kernel is very important for calculations, and like the end of this presentation, I would like to mention briefly that certain support given by the CNPq, Pesquisa, and the UFI University. Otero is the CONACYT, Panthers to CAPES, and Joan to the CONACYT as well. This is basically what I wanted to show you today. Again, I would like to mention that I am very pleasant, and for me it's a great honor to be together with you in this important seminar. I thanks to Sandra, Juan, and Mauri once again, and all the participants for the attention. Okay, thank you very much.
Thank you very much, Reinaldo. It's for us also a great pleasure to have you here today. And I will open for questions. And I can see that we have a question here from Hernan Cortez. He wrote, could you give me a practical application or practical case, please? Could you keep your slides? Maybe yes. It's better if
No, I will do that.
Okay, keep it sharing.
Sharing.
Okay.
I think that it is.
Renan is curious about the practical case application.
Yes. Can you see the screen?
Yes.
Okay.
Yes.
One application, Hernan, trying to let's say explain a little bit. Well, here, trying to do that, we consider dermis, the skin, in particular dermis. Dermis is the skin. Skin, like you know, the skin is a typical viscoelastic problem, but let me tell you that viscoelastic in the skin obviously is non-linear problem. But trying to, let's say, to analyze a possible application like the first step, because this is a linear model, which is, let's say, a limitation of our modeling, because we are considering only linear, and the skin in particular is non-linear in the whole range, or practically the whole range of the behavior. But we have an idea of possible application here, collagen with ground of substance, given here the parameters, Young module and Poisson ratio. We use the Prony series for the calculation of the parameters for a mice dermis, like I mentioned, and trying to, let's say, to make a concrete model. Then we introduce that stratified function that provide that wavy effect in the structure. And this is more or less a representation of the dermis, with the reported here in this paper, the chairman and et al. Here this realistic case of dermis, and it is idealization. And then the idea is, now we show you only two relaxation moduli and two inverse moduli. But in general, we can calculate the whole set of relaxation moduli. Once you have the relaxation moduli, you are considering the homogeneous materials. And then when you have all these materials characterized, you can find a boundary value problem, because you are transforming a very heterogeneous problem to an homogeneous problem, and using the homogeneous characteristic like provided by asymptotic homogenization, you can stay a mathematical problem, boundary value problem in general, and you can solve it. Like a stress or a stretch or twist, whatever is the problem, you can solve it in principle. It reduces the time for the calculation, because using finite element method, you can do it, of course, but the time, the computational cost is high. And here we are reducing the computational cost. This is the advantage. Disadvantage is that asymptotic homogenization has the limitation. You cannot solve any problem. You can solve certain problems. Well, in particular, this is one application. The other application is here, like I mentioned. We calculate for the Visco-piezoelectric 2 parameters. And if you find in the literature here, the KT and KP are the electromechanical coupling coefficient. And the electromechanical coupling coefficients for ultrasonic require to be large, because in that case, you see a contribution, very good contribution for the design of ultrasonic transducer, because in particular, it is important to have a very high values of KT and KP for catching the image in medical application. This is 2 typical examples. Okay?
Okay. Thank you, Reinaldo.
No.
I think if you the people in the audience, do you have other questions? You can write in the chat or open your microphone. No? No. I think no more questions. Okay. I think we don't have. I have one question, a small, very, very quick question. At the end of your presentation, you put a example. I think this is example 5, where I saw some mesh generations. I did, yeah, this one. Here we are using this three mesh generation, mesh, 3 types of mesh, and you generate this meshes and using the console multiphysics.
Exactly.
It's a software.
Exactly.
And how many points you use here? You are in a very big simulation.
Right. You are talking about, let's say that in general, it was, first of all, the community of console community is very, very close. It's difficult to find when you have problem with the code implementation, or you have problems with that. The community is not very, let's say, friendly. Then we need to work hard in the, let's say, in the solution of the problems. This is, I would like to say that Oscar Luis, who was in France getting the PhD, together with Professor Levon and me, and they have in the lab the console, which is very expensive as well. And look at that, the algorithm need more than 40 points for the Laplace space. And in particular, for, let's say, for that mesh, the generation of that mesh is more than 2,000 points used.
Mm-hmm.
Which is a computational cost, Sandra, was very high, really.
Yeah. Yeah,
but
I think so.
they do it. They do it.
Okay. Thank you. Thank
Oh.
you, Reinaldo. Thank you for your very nice talk, and I hope you will be here in another opportunity. Okay.
Thanks to you. Thank you.
So I will stop the record, and then I will call Professor Giovanni. Wait a minute.
Razani is here.
Yes. Can you hear me?
Okay, good.
Okay. Let me share my screen.
Please. Já posso começar, Sandra?
Um minuto.
Tá.
Deixa eu ver
Você me avisa,
se...
né?